All right, welcome back everybody to Simple Harmonic Motion. Today we are going to be talking about energy. A lot of this you've seen in the energy unit, but we're going to be having a more of a simple harmonic motion perspective. Okay, let's go move on. All right, so energy in simple harmonic motion. Okay, so when the mass is at the limits of its motion, example, it's at its amplitude, either the negative amplitude or the positive amplitude, the energy is all potential or elastic potential energy. Okay, so when it's all the way squeezed at the amplitude over here, or all the way, compressed or pulled all the way over here, that means all of the energy is elastic potential energy. And if you remember the formula for elastic potential energy, that's going to be 1/2 kx squared. But in this term, the x is the amplitude, so we have 1/2 ka squared. Okay, next part. When the mass is at the equilibrium point, the spring is not stretched and all the energy is kinetic. So right here, it's not stretched at all. This is the fastest that it's going. And that means that all of the energy is kinetic energy. So the total energy is just kinetic energy. And if you remember that, kinetic energy is equal to 1/2 mv squared, just like this is showing. When the mass is in between the equilibrium and the amplitude, it is both moving and it is both stretched or pulled. So like, for example, right here, the spring is pulled a little bit, so it has elastic potential energy, and it's moving a bit, so it has kinetic energy. So it's not at its amplitude, so we're just going to have x here. But this is what we're going to use when it has both. Okay. We're going to do a few problems with this, so it'll make more sense with that. This is a good video to kind of visually see, so I suggest watching it. Okay, here we go. A block of mass 2 kilograms is attached to a spring. The spring constant is 200 Newton meter, and the block is free to oscillate 3 meters from the equilibrium. Let me just write some things down just to simplify. 2 kilograms, and this is 200 Newton per meter. What is the total energy of the system in any given time? Okay, so for this, to find the total energy, I'm going to just say, okay, if it's at its amplitude, what is the energy going to be? So I'm just going to do the total energy is equal to the spring when it's at its amplitude. So that's going to be all elastic potential energy. It's going to be 1/2 kx squared. And the x here is the total energy is going to be at the amplitude. So the x is just going to be the a of the amplitude. So 1/2 k, 200 Newton per meter. And when it's at its amplitude, it is 3 meters from the equilibrium. So I'm going to do 3 squared. And let me put this into my calculator. 9 times 200 times 0.5. And we get 900 joules. So that is the total energy this thing has all the time. So while it's oscillating back and forth, there's no friction, so nothing's going to be stopping it. It's going to be going back and forth forever. And anywhere along this path, it's going to have 900 joules of energy. Sometimes it might be all kinetic energy. Sometimes it might be all elastic potential energy. And a lot of times, it'll be some elastic potential energy and some kinetic energy. Okay. Part B is, what is the maximum velocity of the mass? Okay. So that means we're looking for how fast is it going right at this point right here. Because that's the fastest point. That's the velocity max. And we know that is when all of the energy is kinetic energy, because the spring is not pulled or compressed. Or stretched or compressed. Okay, so we know the kinetic energy is equal to 1/2 mv squared. And remember, right at the fastest point, it's all kinetic energy. So that's going to be 900 is equal to 1/2 the mass, which is 2. And this is the velocity max. And then let's put this into 900. Well, 1/2 and 2 just cancel out, so just do that. So I'm just going to do the square root of 900. And we get 30 meters per second. So that's the fastest this thing is going to go as it oscillates back and forth. Okay, part C. When the block is 1 meter from its equilibrium position, how fast is it moving? Okay, so we want to know when the block is right around here, 1.5 meters. Okay, we want to know how fast is it going when it's over here. Okay, so we know when it's right here, some of the energy is going to be elastic potential energy, and some of the energy is going to be kinetic energy. So we should know 900 joules of energy, some of that is going to be kinetic energy, and some of that is going to be elastic potential energy. So let's fill in what we know. So we know the total energy it has all the time while it's oscillating back and forth is 900. We want to know how fast it's going at that point. So 1/2, mass is 2. We don't know how fast it's going, that's what we're looking for. For the elastic potential energy, 1/2 K, we know that's 200, and we know it's 1.5 meters from the equilibrium. So I'm going to do 1.5 squared. Alright, so let me try to simplify this as much as possible. 900 is equal to V squared, these cancel out, plus 1.5 squared times 100 is 225. Okay, so I'm going to do 900 minus 225 and find the square root of that, and I get the velocity is equal to 25.98 meters per second. Okay? And we should know that, it should be slower than the fastest speed, which is 30 meters per second. So, looks good. Part D is, at what point is the block moving the fastest, and at what point is the block moving the slowest? So, we already talked about this before, but right here, that's when it's going the fastest, that's when it's all kinetic energy. And where is it moving the slowest? It's going to be at the amplitude. That's when it comes to a complete stop, so there's no kinetic energy, and it's all elastic potential energy. Okay? Alright, moving on. Example number 5. A simple harmonic oscillator has an amplitude of 3.5 centimeters and a maximum speed of 26 centimeters per second. What is the speed when the displacement is 1.75 centimeters? The object has a mass of 3 kilograms. Okay, let's draw this out, just a little diagram. And then this, and then we'll have this position 0, and there's an amplitude of 3.5. Oh, let me just make that into meters. Gonna be 0.035 meters, and over here too, 0.035 meters. Okay, and the fastest it's going, I'm going to put V max, is equal to 0.26 meters per second. Okay. Anything else? What is the speed when the displacement is 1.75 centimeters? Okay, so we want to know when the block is like over here. I'm going to do 0.0175 meters. We want to know what the speed is. Okay, great. The first thing I'm going to do is I'm going to find, this is 3 kilograms. The first thing I'm going to do is I'm going to find what the total energy is. And I can do that by trying to find the energy at the amplitude. So the total energy is going to be equal to the elastic potential energy at the amplitude. So that's going to be 1/2 K. Ooh, K is not given. Okay. Oh, well, it gives us the maximum speed. So the other way we could find the total energy is not the elastic potential energy at the amplitude, but we could also find the kinetic energy when it's at its max. Okay, so let's do that. So 1/2, the M is 3, and the fastest it goes is 0.26 meters per second. So let's figure that out. Squared times 3 times 0.5. And then we get 0.101 joules. Okay, so that's the total energy. Now we can use this to find what the spring constant is, because we don't know what the spring constant is. Okay, so I know that the total energy is 0.101 joules of energy, and I can find what the spring constant is when it's at its amplitude here. So I'm going to do 1/2 K, which we're looking for, and the amplitude we know is 0.035 squared. So let me do some math. 0.101 times 2 divided by 0.035 squared. And we get K is 164.6 0.9 Newton per meter. All right, now finally we can try to solve this. Okay, so we know the total energy is 0.101. We know when it's at this 0.175 meter mark, there's both elastic potential energy and kinetic energy. So 0.101 is going to be equal to 1/2 K, which we found, 164.9, times how far it is, which is 0.0175 squared, plus 1/2 M, and then V squared. That's what we're looking for, V. So let's simplify things. 0.101 is equal to 0.0175 squared times 164.9 times 0.5. And this is going to be equal to 0.025 plus, I'm going to do 1.5 V squared. Okay. 0.1 minus 0.025 divided by 1.5 square root. And we get velocity is equal to 0.225 meters per second. Whew. That was a lot. That was quite a bit. So if you had a hard time, watch it back. I might have gone a little bit fast with that. So if you weren't able to follow, take it one step at a time, watch it back. All right. I think last one here. Well, we'll see. Okay, the following diagram shows a spring oscillating from 0.02 meters from its equilibrium position. Okay, find A, the maximum and minimum velocities attained by the glider. Well, I guess luckily for us, we know the minimum velocity, that's just going to be equal to 0 when it's at its amplitude. And then we have a lot of information here. The spring constant is 200, the mass is 0.05. So we can use this to figure out the maximum velocity. Okay, so let's find what the total energy is. And knowing that when it's at its amplitude, that's going to help us give us the total energy. So I'm going to do 1/2 K 200 amplitude, which is 0.02 squared. Let's see what that gives us. 0.02 squared times 100. So this is going to be, the total energy is going to be 0.04 joules. Okay, I'm going to use that now to find the maximum acceleration. So 0.04, that's the maximum, that's the total energy. It's going to be equal to 1/2 the mass, 0.5, velocity squared. And that velocity is going to give us the max velocity, because I'm saying all of the energy is going to be all kinetic energy, and that's going to be at the fastest point, the equilibrium. Now let's find what that is. So 0.04 times 2 divided by 0.5 square root, and I get 0.4 meters per second. So that's the fastest. So 0.4 meters per second and 0. Okay, part B is what is the maximum and minimum acceleration. So we didn't talk too much about forces in this chapter yet, but we should know that right all the way at the amplitude, we talked about this, the force is at a maximum. Okay, so whether it's here or here, the force is at a maximum, and the acceleration is at a maximum. Whenever the force is at a maximum, that's also when the acceleration is at a maximum. And when it's at its equilibrium position over here, that is when the spring is not compressing it or stretching it, so the acceleration is going to be 0. So there is no net force on it, so the minimum force is going to be 0, and the minimum acceleration is going to be 0. Okay, but let's now find what this maximum force is going to be. We're going to have to recall Hooke's law, where we know that when it's stretched, we have kx is equal to the mass times acceleration. Well, yeah, k. So when it's over here, it's all, the force is all by the spring, so the force of the spring, and we know the force of the spring is equal to kx. Okay, so k is given to us 200. When it's at its amplitude, that's when it has the maximum amount of force, so that's going to be 0.02. The mass is given to us 0.5. and then we can find the maximum acceleration. So let's do that. 200 times 0.02 divided by 0.5. And we have an acceleration of 8 meters per second squared. Okay? That's going to be the maximum acceleration. All right. Part C. The velocity and acceleration when the glider is halfway from its equilibrium position. Ooh. So this is going to be a little bit tricky. Well, I shouldn't say tricky. It's just going to take a while. Okay, so we know when it's halfway, that's going to be like here. That's going to be 0.01 meters. And what do we want to find? Velocity and acceleration. So maybe let's find the acceleration first. We're going to use the same thing. The force of the spring is equal to kx. Okay? So, and we also know that the force of the spring, since it's the only, like, that's what the net force is acting on the spring, is going to be equal to ma. So k is equal to 200. That's the spring constant. X is 0.01. That's how far it is from the equilibrium. Mass is equal to 0.5. And now we're looking for acceleration. Okay, 200 times 0.01 divided by 0.5. And that's going to be 4 meters per second squared. So that's the acceleration at this point here. Now let's try to find the velocity. Okay, so I know that the energy while it's oscillating is 0.04. We've discovered that before. Okay, so I'm going to say 0.04, and some of that energy is going to be elastic potential energy, and some of that is going to be kinetic energy. Whoops. Kinetic energy. Plus. So let's figure this out. 0.04 is equal to 1/2 k, which is 200, x, which is 0.01 squared, plus 1/2 the mass, which is 0.5, v squared, which we're looking for, v. Okay, let's simplify this a little bit. 0.04 is equal to 0.01 squared times 100. So this is 0.01 plus 0.2, oops, 0.25. 0.25 v squared. And then let's find v. So 0.04 minus 0.01 divided by 0.25, and then the square root of that gives us 0.35 meters per second. Ooh, that was a lot. All right, so that's what we got. All right, let's keep going here. I'm gonna erase this part here. Okay, so part D says find the total energy, kinetic energy, and elastic potential energy at this given point. So we know the total energy is always going to be the same as it's oscillating back and forth. And that's going to be what we found before, which was the 0.04. So I'm going to do total energy 0.04 joules. The elastic potential energy is going to be equal to 1/2 k 200 times 0.01 squared. So let's do that. 1 squared, 100. Oh, and that's 0.01, which we found before. Yeah, we found that right here. Okay. Whoops. And then the kinetic energy is just 0.04 minus 0.01. But we can also just check our work. We could do 1/2 mass, which is 0.5. The velocity squared, which we found was 0.35 squared. 10.5, 10.5. And we get, yes, 0.03. Sorry, 0.03 joules. Okay, great. Part E is if the block oscillated from a further point than 0.02 meters, how would this affect the block's maximum and minimum velocity? Okay, so let's say it oscillated not from here to here, but here to all the way over here, okay, more than 0.02 meters. How would this affect the maximum and minimum velocity? The minimum velocity would be the same. It'd be 0. But the maximum velocity, since it has more energy now going back and forth, it'll be a lot faster in the middle. Okay? The maximum velocity would increase, but the minimum velocity would be 0. Okay, so that's pretty much it. Thanks for watching, everybody. I'll see you with the next one. Bye.